Hey everyone, my name is Gabriel Quaresma and I'm a software engineer uh, mm, at CodeMiner 42. And today we're going to talk about in this brown bag about optimizing text filtering with Trie data structures. Yeah, by me. Right, let me put in the slideshow here to be better to see here. Okay, right, so let's start. The agenda on this presentation will consist on uh, show how to build an API to detect forbidden words in text, right? This will be our user case to apply this data structure. But first, we need to see why we need to use this data structure, right? So yeah, we need to start with an initial solution that will be the more easy and how can I say more simple solution. You can say stuff like this. Uh, and a better solution using a try, a better in quotes. We will see why better in quotes. Operate our API using a try, right? And measuring performance, a benchmarking to see the difference between the two approaches. And wrapping up will be like to recap everything that we saw in this presentation, right? So let's go. And right, so building API to detect forbidden words in text. Uh, this API is based into the features from many social networks that use some kind of moderation to filter the allowed and not allowed words that can be sent in a comment section, for example, in YouTube videos or Reddit comments, stuff like this, or in a post on LinkedIn. There are some words that cannot be sent, for example, and this API will be this API here would be good to illustrate this case and how to apply this data structure. But first, let's go to the initial solution first. But first of first, let's see how can describe this API. Like the endpoint will be just a post method, flag words, a payload that you can send a text, right? Text content, for example, can be a comment or can be, yeah, I don't know, a text for another book, stuff like this. And the response will be the array of the forbidden words found in the text, right? So in this API was constructed and you can was developed using Ruby on Rails framework, right? The language Ruby, and but feel free to implement by your own in your machine using any other language that you most like. It can be JavaScript, can be I don't know Java, C sharps, I don't know. So yeah, the controller is so simple. You just expose a method that will be our endpoint flag that we call a service that you only pass text in the forbidden words array and return the JSON with the flag words. And the forbidden words is on a private method here that is static that you are uh, define a simple array with only three forbidden words full by path, but can be this data could load data from an external API or from the database, right? Cool. So yeah, our service is so simple. It's only passing a text in the forbidden words that I said before, and the text will be handled like to split the text content using the space and break uh, the words to return an array, right? And here we're doing a map to that case to make more easy the comparison if you have and detect the word that you have or not in our comparison, right? And in the flag words are very simple. The feature is so simple. You are just using the include method from the array class from Ruby, and you can think now, okay, yeah, it's a good solution. We solve our problem, and right. But let's see the time complexity and the space complexity. The time complexity is ON. Why? Because N is the length of the array. In the worst case, array includes must scan the entire array to either find the element to confirm it doesn't exist, right? And as you can see here, if you go to you can scan this QR code to go to the GitHub of Ruby project, like the source code from Ruby language that we use C to implement many of methods from many structure like Rash, array, and many others. In this case, the array includes method, as you can see in the implementation, really use a loop to iterate over the all array to check if it has the element that you want to find. And for each element, the comparison operation equality check is performed with a type typically or one for primitive types like numbers or strings, assuming constant type string assuming constant time string comparison for fixed length strings. But the space complete is O1, excluding the input array, because this solution we only use the input that we receive from the forbidden words without handle. You only use this input to find the forbidden words, right? So you can think that for a large dot set can be very, very slow, because if you have 1 billion of elements, yeah, it would be take so much time to find the word that you want. So we can see you can see, I can demonstrate this to be more clear, I think, using the scalar draw here. And as you can see here, we have this array, this simple array with the forbidden words here, like open, good, cutie, great. You only have here 1, 2, 3, 4, 5 words, and you can think, okay, you can try to find open first. You just need to treat one. It's okay. It's the best case, but sometimes you can have, for example, we need to find grape, and we need to, for example, uh, we need to iterate like 5 times, 1, 2, 3, 4, 5 to find grape. But it's okay. 5 times is, yeah, not take so much time. But you can think here, for example, if you have an array with 2 million of words, would be not so good to find the word that you want. And if this word are in the 1 million position, is a lot of uh, time to iterate until find the word. So not so good. And go back to the slideshow here. I think now is so much clear why it's not the best solution for case that you are using a large data set. Because thinking about in a more realistic case, for example, we have in each country a lot of we have a universe of words that cannot be sent in a comment, for example. And yeah, in this kind of case, we need to choose a better solution, another approach. And this will be the approach that we see today. That will be using a trie, the prefix tree, right? Prefix tree is a data structure that is a tree, right? That store the the forbidden words that in our case, each character for each word that you want to find, and a node in the tree, right? And to build a tree, the time complexity is m multiplied by n, because n is the number of the elements in the array, right? And m is the average length of the elements, the length of the string that you want to insert, right? And each element is inserted into a trie by transversing or creating nodes for each character or unit of the element, right? So you can think about, for example, you have the word all, as you can see here, that you are inserting the character R, L, L to form all, and you have art too here that use R, L, R, A, R, and T, right, to store and act, for example, another word. Oh, not act, arc. Have another one, port, for example, that are storing the P, the O, the R, the T in the tree. So this is the complexity. And the space complexity is like the worst case where the try store each character of each element. If many elements share common prefixes, the space usage can be significantly less. So you can think like you have a lot of words that start with R, L, of RL. You have a more a less space used, right? you have a lot of words that use the same prefix as I said before. Right. So and the session try, the time complexity is OM because the time complexity is not looking into the length of the forbidden words array, but the word that you want to search, the size. So, for example, if you want to find a word like all, you only need to iterate over this word like 3 times because we need to find A, L, L. So it's constant because you are trying to search this word, we don't need to find the all array or most part of the array to find this word. We only need to find the characters that form this word, right? Is simple. I think is more simple, is more efficient to find this word and be more fast to the end of the day, more fast. Cool. In the space complexity is one for the search operation itself, including the try extruder, right? Is as I said before, because you are storing, looking for the word length, right? The string length. And the implementation is simple too. We need to have a class that define a try node, the node that will compose a try, and we only have to initialize a children that is a hash. It is the end of the word that is a flag to identify if you are already insert all the characters of the word, right? In the try class that is composed by try node have a root here and the words that we need to insert on this try, right? The method insert is simple too. We only insert the word. We have the node root here, and we need to iterate of the word that we want to insert, and you need to attribute to the node here in place and find the char by the key because it's a hash. We only need to look up the key, like the key is the character of the word. And if you don't have, you only need to initiate a new try node. And in the end, you only need to set is the end of the word as a true to indicate that this last character inserted is the end of the word, right? Uh, and search is very similar. We need to iterate of the word that we want to search. And if we don't have the word here, we need to return false. That indicates to the service that is consuming this data structure that is the word is not found. And otherwise, we return true because we reach on the end of the word, right? And okay, so now we need to update our API with try. Cool. If you want, you can scan this QR code here to go to my GitHub and see all code after this presentation of this. And the service we need to has a little changes here, like the try that we need to add to use as input the forbidden word that you want to search in our text and create a try here in memory. And now we only need to change here the flag words, like selecting the words that you want to handle and search each word from the text. Cool. Yeah, I think it's easy. It's very simple the change. And now measuring the performance, the benchmark. This benchmark you can stop the video if you want, like to see more with more time and with more calm. But here is comparing the time. We see the time is with the forbidden words, like until start with 10 words, to 10 forbidden words until 10,000 words here. And the try total time, the average time using try, and in comparison with our include method total time and our include method average time to run. I know that's a lot of numbers here that we are looking now, but I think the next slide will be more easy to see the real difference between these two approaches. Yeah, the blue line, you can see the try implementation, increasing the number of the forbidden words, and the I axis is the average time per run, seconds in log scale, And as you can see, when you are using a small data set of words, the array include is much faster. It not so much faster, but yeah, it's faster than the try. But as we are growing the number of the forbidden words to search, uh, you can see the time. Yeah, the average time is growing linear, and you. But in the try approach, you can see that yeah, this is like is almost constant during the time during the independent of the number of the words that is growing or not, right? So you can see. So in the end of the day, when you are handle a large data set of words of words or number, it's better choose a solution like prefix tree, the try. But there are another data structures that can be used, but this one is a good one to choose. And wrapping up the presentation, uh, right? So this table is just compare like in terms of time and uses that you need to to pay attention when you are using the two approaches. So the search time complexity in array includes is ON as we see before, because you are looking in the array includes by the length of the array that you are handle. Otherwise, the prefix tree is OM because M we are using you are talking about the size of the word that are trying to search, instead of the length of the array. Cool. The setup time complexity is O1 because is none is O1 because we're already using the input that we have. For example, the forbidden words array. Okay, cool. If all right, so we are already using the array. Uh, or else and prefix tree, as I said, I already saw. Oh, fuck. I think yeah, I don't know. The Google Assistant here. All right, so continuing here, the prefix tree, the try, uh, is O M multiplied by N. Yeah, because we need to insert right each word and multiply by the length of the array, right? And each word we take a time complexity according with the length of this word, right? Each word. Space complexity is O1 in the array includes because we are excluding the input array, and the prefix tree is O multiply N for try storage. Uh, yeah, array includes is best for small array, as we saw during the examples here. One of search, and the prefix tree is best for frequent search and prefix carries, right? Uh, and array includes is worst for large arrays, frequent searches, and the prefix tree is opposite, like small arrays, one-off searches. Cool. So yeah, I think that's it. And they're wrapping up. So yeah, I think thanks a lot for your patience here. By the way, CodeMiner 42 have open positions, and feel free to go to our website codeminer42.com to see the positions and to know more about our company. So yeah, thanks a lot, guys, and give the like on the video and share with your friends. And feel free to send questions in the comments. And or yeah, I think that's it. Thanks so much. And yeah, and feel free to reach me on the social networks if you want to have some questions. I will be very happy to very happy to answer them. So